In this video, we're going to look at the generalized inverse matrix. And as a background, you're going to need the singular value decomposition. And I have a video out titled that, because we're going to need it when we prove that a generalized inverse matrix exists. And so let's let A be a given n by m matrix throughout this talk or the video. And definition, if the generalized inverse of A satisfies this equation, then A dash is a generalized inverse matrix. So this is the only requirement that it needs to satisfy to be considered a generalized inverse matrix. Now in later videos, we are going to add some conditions to this generalized inverse matrix, and then we get some additional properties and theorems from it. But in this video, we're only going to assume that it satisfies this equation. So theorem 1 says that for any n by m matrix A, that an m by n generalized inverse exists. And the proof is this: if A is non-singular, then let the generalized inverse equal the standard or the normal inverse. If it's a zero matrix, let the generalized inverse be the zero matrix. And then it's easy to show that both of those satisfy this requirement. Now let's let A be an n by m matrix with rank R. And by the singular value decomposition theorem, A can be broken up into these three matrices, where P and Q are orthogonal, n by n and m by n matrices, and delta is an R by R non-singular diagonal matrix. So it means there's no zero elements down there. And then the rest of this is zeros. Now, the claim is that this is the generalized inverse of A. And this is for any B, C, and D. So we must show that this generalized inverse satisfies the conditions for a generalized inverse. So let's do that. So we start out with this, and then we plug in what we know. So this is A by the singular value decomposition theorem. We're claiming this is our generalized inverse, and this is A. Now Q and P are orthogonal, so that makes these the identity matrix. So those essentially go away in this matrix product. Now we multiply these three matrices and notice that there's a lot of zeros. So after you do that, you get this matrix. Q prime comes down P. Now delta inverse, that's the identity matrix, and then times delta, so you get it back. But this matrix here, this matrix product by the singular value decomposition theorem is what we're calling A. So it does satisfy the requirements, and this is a generalized inverse. So why is the generalized inverse useful? And it's useful in solving AX equal B when A is non-singular and the system of equations are consistent. Okay, and consistent means that B is actually in the column space of A. If B is not in the column space of A, then a unique solution doesn't exist, and we have to find something that's, quote, close enough. And maybe one approach is the least squares approach. And in the next video, we'll look at what's called a least squares generalized inverse and solving that. But here, we're assuming that A is non-singular and the system of equations are consistent. So theorem 2, if we have this system of equations, AX equal B, and it's consistent, then the solution, then this is a solution if and only if it meets this requirement too. So the proof is we assume this is true, and then we assume this is true, and so that must be true. And then we go the other way, assume this is true, and that must be true. So let's go this way. We assume this is true, and we pre-multiply by A generalized inverse to both sides, And since it's a generalized inverse, that's A. And then since the system is consistent, we actually know that that's B. And then this requirement is true. Now, to go the other way, we assume that this condition's true. And if we let X hat be the generalized inverse of A times B and substitute that in, well, then it's true. So that's a solution. And so we're finished. And so what's the consequences of this theorem is if you have a system of equations that are consistent and you find the generalized inverse of A, and then you take it A dash, or, B, and if you get B back, then you know that this is a solution. So it makes hunting for solutions much easier. So now we want to show that a solution in this setting is not always unique. So we have a system of equations and it's consistent, and A is non-singular. The solution A hat or X hat is not always unique. When we say not always, it can be, depending upon, the properties of A. And actually the properties of the generalized inverse. But in this video, it's very generic. It only has to satisfy that one requirement. So let's let A dash be a generalized inverse of A. Then for any m by 1 vector y, this is a solution. Okay, and I'm going to call it x hat y, because this solution is actually a function of y. So you put in any y vector and you get another solution. Okay. So now let's check it. So let's A x hat, and then we substitute this in for x hat. We get this. So then we distribute the A, and we get this. Now, since the system is consistent, we know this property holds. So then we substitute B for this, and it comes down. And then we multiply the A into this. Now, since it's a generalized inverse, we know this property holds. So we get A minus A. But that's 0. So this goes away, and B, we get B. So that says that this is a solution to the system of equations. And B and our solution is not always unique. So anyway, that's all I have for today. Hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.